Two identical pith balls hanging from strings are each touched by a charged glass rod and then attain the equilibrium state shown in the diagram below. Once the glass rod is removed from the area. Okay, so obviously they're sort of being held apart in a strange little, circumstance. What's holding them apart instead of just being held vertically, kind of like touching each other, right? Which is what you would imagine if you just kind of walked up to these two, right? So what's holding them apart from each other? Yes, but like holding is a type of pulling, which is a type of pushing, which is a force. What force is holding these things kind of like, because this word is super, super important here, right? Equilibrium. What does that mean about this system? Ooh, no, not necessarily the start, because it says they're touched and then attain the equilibrium state, right? So so this is a sort of after some time it reaches this state, right? If I drop a ball and I catch it like a split second after dropping and it's in the air, is it fair to say that that thing's in its equilibrium state? So equilibrium, you mean kind of means things are equals in some way, right? Like things are balanced, but what is balanced? What is equal? What does it mean to be in equilibrium in terms of forces? Okay. I would be with you if we hadn't talked about this subtle little thing about moving but not changing my motion, right? So, what do I mean by that? Why am I being picky here? It's because this comes from F net equals MA. And so it's not about movement. There's no V in this equation, right? Because if I could throw a ball up in the air and I catch it right at the moment that it's at the top, it's not moving there. But it's not at equilibrium because the way I can prove that is a split second later, it's been moved to a new spot by the forces that are there, right? What's moving a ball when it's moving up and then coming back down? What's the thing that's not at equilibrium? What's the force that's there that's not balanced? Gravity. So to be at equilibrium means not moving, but that the acceleration is zero, which means F net is zero. Okay? So that's going to be the foundation, and the word equilibrium means that. Like when you reach a state of equilibrium, it means that all the forces are causing you to sort of like not really be able to move anywhere because as soon as one pulls you one way, the other one pulls you up equal and opposite way, right? An easy explanation of this or something example of this is a tug of war scenario where they're not moving. Both sides are putting a lot of force in, but they're not moving. Why are they not moving? Why are they in equilibrium? Because they're equal, right? So it doesn't mean there's no forces. It doesn't mean they're not moving, right? That's a subtle one. That's a subtle one. Maybe like 2 years ago I would have given you that without even mentioning it, right? But now we have to be careful because V equals zero doesn't mean that A is equal to zero, right? Like those two things are different, right? Just like my position being at zero doesn't say anything about my speed. Just because I cross the zero spot doesn't mean I'm not running really fast and will soon be past it, right? It's kind of the same relationship with velocity and acceleration. Just because my velocity is at this spot in this 1 second doesn't mean it's not going to be something else later, right? When the ball starts to move down again. Right? Okay, so all of that to say, we can now do F net equals zero free body diagrams on these things. So they you're sort of told that they each have the same amount of charge, right? So did you sort of like choose a value there? Yeah. Yeah. Like, did you pick a particular value, or did you just sort of like keep it as Q, or have you like attempted this one yet? Okay. Okay. So now that we have that little bit of information, right, which was almost directly given to us from the question, equilibrium means F net equals zero. So there's a reasonable kind of like crumb for us to follow. Yeah? Okay. So I want to leave you to it. Like I want to start to build some independence in our time together, right, where we can kind of check in a little bit, but not necessarily like you can start to do these on your own, right? And kind of confirm with me because part of what we have to build together is that confidence because you do know a lot of this stuff, right? And not knowing where to attempt it is the first step of every problem. That's should like that's a hard feeling, but it's gonna happen almost every problem from now on, right? You're in the tough world of physics, so. So I'm gonna start to build, slowly kind of try to catch up to you. I'll build my free body diagram and hopefully we'll sort of like, if you are struggling, you can kind of check in with what my procedure is as well. Okay? Do you have your free body diagram for one yet? Okay. How many forces do you have on it? Nice. Okay, which ones are they? Yeah. Yeah. Good. Um, yeah, I mean, anytime we have a two-dimensional force, you cannot do a two-dimensional F net. You have to do F net X and F net Y, right? So anytime I see a free body diagram with slanted or diagonal lines, not just up, down, left, rights, I have to break them down. Okay? Is that an attractive force or a repulsive force? What's your proof? But the distance arrows, like you've seen this before, where I just say like, this person is at this height, right? And I do this with the two arrows. You've seen that before, right? So that's all that is. There's better proof. They tell you that it's at equilibrium, right? Can this system that I've drawn here be at equilibrium? Remember, what does equilibrium mean? It means when they're all balanced. And remember, as a physicist, your ability to evaluate vectors is only in the x and only in the y, which is only up, down, left, right. So are there ups and are there downs? Are there ups and are there downs? So that means that it's possible for ups to cancel downs, right? Are there lefts and are there rights? Not the way I've drawn it, right? They're both going to the right, the two vectors that are horizontal, right? The way I've drawn it here. You see it? Oh, wait, can you not see my screen? Oh, no. Okay, wait, one sec here. Oh, okay. Here, let me. Can you see that? Okay. So do you see this? Was that new? Okay, sorry. Okay, so this is, how I drew it, right? I was asking, is that an attractive force? If it was an attractive force, it would be that way, right? And we were talking about ups canceling downs. There are ups, there are downs, so they can cancel. Are there lefts and are there rights in this diagram? No, there's only rights, right? So there's no way that this thing can be in equilibrium, right? So that's one of those zoom out things that you can do, right? No matter what's happening in the problem, you can look at any free body diagram and say whether it could be in equilibrium. You don't know the size of anything. But if it's only rights and only downs, zero chance of it being in equilibrium. That thing has to move down and right, right? Okay, so that's also how you can sort of answer this question. The other thing is that they're moving away from each other, right? So they wouldn't want to move away from each other if it wasn't repulsion. So I'm going to use FQ. Is that okay? Or do you use FE? Okay, I'll use, okay, no problem. So I'll use FQ. Okay. I guess it looks a little bit like the G, but okay. So that's the left ball, right? Are you comfortable saying that the right ball is going to be kind of like the mirror image of this? Yeah? I think actually I can do that. I think I can this. Oh, 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 oh. Yes, can I flip it? Okay. So the letters obviously get flipped, but it looks like that, right? Okay. So what do we do now? You already had the intuition. Mm-hmm. I like that face. That's good. That's good. But I mean, just for one of them, like the right one doesn't have any influence on like this tension. These are two separate strings. Yeah. So the tensions are not equal. They're not the same, right? Well, I mean, they might be, but there's no obligation for them to be, right? So, okay, so we have to break down FT into components. How do we do that? Good. What was that? But? There's a but? Yeah, yeah, yeah. No, you're right. This is a right angle triangle, right? So we could do SOHCAHTOA. Okay. So let's do SOHCAHTOA then. Which theta do we know? So we need a theta for SOHCAHTOA, right? Do we know a theta? We don't know the angle that this string is at, right? That's the problem. Do we have information to find it though? Why? Yes, nice. Beautiful. Yeah, exactly. So this is a right angle triangle that can take out. But then we want to be very careful about which one is the actual theta that we're kind of like looking for. Well, first let's sort of solve this triangle, find kind of like both angles, and then look back to our FT and see what we're going to do. Okay. So L, and what is this here? Yeah, it's D over 2, right? Good. Okay. So we'll grab that. And that is 10 centimeters. Centimeter. What are we after? Are we after a length? So if, yeah, so we're looking for an angle, right? Which is unitless, or it has a unit degrees. It doesn't use the units of length, right? So the centimeters will cancel with the centimeters just like the meters will cancel with the meters. So it's always a good practice. Like I like that instinct to sort of say like, hey, get these centimeters out of here. They've betrayed me too many times. I want to get them out, right? Because I'm never going to go wrong. Even if I do this, and that's a sort of decision for you to make about your energy investment, right? But just to answer your question, we don't have to. The question you should ask is, what unit am I looking for? Does it contain the units, or do my meters cancel in some way, right? Because if the meters cancel, then somehow the centimeters will probably cancel, right? But where that goes wrong and where that becomes a waste of time is if you ever square it, it totally goes out the window and then you're betrayed and it's just a waste of time. So it's a good practice what you did to sort of like say, okay, let me just turn these into meters right away, right? But yeah, we don't necessarily need to for this one. Yeah, I love it. That's good practice. Like you're gonna save yourself so many silly mistakes over that, and it's worth it to just continue the practice for these types of problems. And same with our mass, right? Oh, right. Okay. So we gotta build it with all of our standard units. Don't be prejudicial about meters just because it's your old friend. We got newtons, kilograms, seconds, and meters, right? Meters per second square, and most of them others are that kind of manipulation of those units, right? Okay, so then we need to add how many zeros in here? We need to add 3 zeros in there, right? That. So it's 1.2 times 10 to the negative 4. Is that okay? Say that. Okay. Okay. So do you feel like you sort of see where to take it from here? Okay. Do you want to try it, or do you want to like sort of tell me what your plan would be to check in, or how do you feel about sort of trying this? Mm-hmm. Yeah. Mm. Yeah. Yeah. And our F net equations, right? Good. Okay. Yeah, it sounds like you have a good path here. Okay, so I'll give you a couple minutes and see if I can kind of catch up to you as well. So I'm not disturbing. Something up? How's it coming? Okay. How? Good. Right? So we don't even have to sort of like solve there, right? And being able to see past solving there and being able to sub it in without it being solved is a big step. So just ft, which one is cos theta, which one's sine theta? Okay. Well, it depends on which is your theta. So which is your theta here in this triangle? Is it the top right or the bottom left? The orange or black? So then cos means adjacent. And what's adjacent to that angle? The x or the y? No, no, no. The bottom one here, adjacent to this angle, right? So that angle, if we're going to do the cos, we can use this angle here, or we can do the sine of the other angle. So that one will be sine, because this is my FTY, right? In this triangle here, this was the theta you used? Okay. So then, did you use cos? Did you use cos inverse in this equation? Yeah, or sine inverse, or tan inverse. What'd you do to solve for theta? Oh, okay, wait. Sine inverse means opposite over hypotenuse. So in your right angle, like, do you have a right angle triangle drawn on your page? Okay, can you show me the picture of that? Because I think I might be just causing more confusion than needed. Um, sorry. Okay. A little bit the other way. No, that way. More into the middle. Yeah, sorry. Perfect. Yeah. Okay. Okay. So what I see here is a diagram without a theta, which is the problem, right? So add your theta in to your FT diagram, because you do have your theta in your other one, but then you didn't include it in this one. And those triangles are not the same orientation, right? So you want to make sure that you have the right orientation of your triangle, meaning like it's slanted up and to the right and the right hand corner is in the bottom right, right? Rather than this triangle, which is like slanted up and to the left and the right hand corner is in the bottom left, right? Okay. So where is your theta on this diagram then? That you've drawn, that you've picked? Because you can do it this way. You just have to make sure you label your theta right, right? So which theta did you pick here? And I think what's also making this harder is that we didn't do it to scale, right? We made it look like a classic like 45-45, right? Which is making it, I think, harder to tell which is the skinny side, which is the long side, right? Which will be the taller side? Which will be the taller one? Which one will be greater? FTY or FTX? Oh, zoom out moment. Zoom out moment. Look at your tension. Is it going more up or going more to the side? Your tension force. More up or more to the side? Well, your tension. It's going, for every 10 that it goes up, it goes 1 to the side. Do you agree? So that rope is pulling more up than it is more pulling to the side. Do you agree? Okay, that's what I meant. It's kind of a hard question to phrase too, right? So that is the zoom out moment, right? That means your FTY should be the bigger one. So regardless of whether you got your cos or your sine or the right angle right or whatever, at the end of the day, if you come to your FTY or FTX, do you have values for your FTY or FTX yet? Did you solve for it at some point? Yeah. What are their, like for their actual numbers? No, because we subbed them in, right? So this is the danger. So, but now that you know FT, right? A formulaic kind of way of like T Y is always the cos, right? Like, yeah, that analysis is like something small that burns you here because you've gotten every step of the way. You've sort of like seen what was coming and be able to do it. That is where you double cross yourself and you don't even notice that you're kind of following along the wrong trail, right? So the check there is that zoom out. At the end of the day, at the end of all of this angle stuff and whatever, when you get values for FTY, FTX, who's bigger? It has to be, if something's pulling more vertically, then that component better be bigger than the horizontal thing, right? Or else it's pulling more horizontal. Okay. Okay. So subtle little thing. Okay, so let's tweak. Make a little tweak there then. So label your theta. So let's get your triangle, this triangle. Maybe it's time to redraw that triangle to be a little bit more representative. So it's got to be like super tall and skinny, right? So let's maybe draw that a little bit more to scale. Do yourself, a service instead of a disservice. It's hard though, because like almost always you can get away with doing this, right? Just doing a 45, 45. So which one are you going to choose to be your theta? The bottom, okay? So that is our theta there. Okay. And no, no, I'm sorry. Yeah, we just, it happens. Yeah. So another thing you could do here, like you already put the work in, right, to find out what the complementary angle is. What's the complementary angle? Yeah. So you could have kept that part and then said, okay, but I'm gonna actually gonna use this angle, and so it's 90 minus that, right? But it's the same thing as sounds like what you did. And again, at that moment, right, you want to check, okay, then does it make sense that this value is so high, right? So yeah, so I think actually you had said that your angle was here, but your angle was actually here. So it actually does work that this is cos, right? And this is the kind of like the hard, or like the frustrating thing, is that if you get the wrong angle and you do the cos, or not the wrong angle, but just the opposite angle and you do the cos instead of the first angle and do the sine, you get the same thing. Or vice versa. If you do the first one, you do a cos, and the second one, you do a sine, you get the same thing, right? So I think it was when I had asked you which angle it was maybe different than what you had on your page. And so that was why I was concerned, but you actually have it right here. Actually have it right. Because it is the cos to be FTY is the cos of that theta, the 5.7, right? But if we were using that angle, it would be the sine of that angle, right? Okay, sorry about that. And it's worth it to sort of, because that's a easy spot where you can kind of, you know, and this is why I wanted to ask what your actual values were, because then that could have put this all to bed of who was who, right? Okay, but then the cos of that angle will be a lot bigger than the sine of that angle, so we're good, right? Okay, so then you solved, or you didn't even need to solve for FT, Y, FTX. You just kind of like threw them in here. And then what'd you do? FT is equal to, okay, so this is over here, right? So you said this was FT cos theta is equal to FG, and so FT is equal to FG over cos theta. Love it. I agree with you. And then what? Beautiful. Okay. Um, sorry, what did you get for that FT? 1.183 10 to the negative 3. 3 times it. Okay, and what unit? Yeah, good. And so, what did you use this for? Because that's the FT. What do we ask for? Yeah, which isn't in any of these equations, but which one's it in? Into the FQ. Oh. Okay, so what's the story over there? Yeah, right? Almost always with physics problems with FNets, we're going to use something in the FNet X to talk about the FNet Y or vice versa. Okay, so tension happens to be the kind of connector here. Okay, so then this is just, so let's just say sine theta. Okay, let's just take away some of this overcrowding here. Okay, so then 1.1, right? Or I guess Ft times the sine of theta is equal to Fq. What is Fq? What's that formula going to be? Do we know Fq? Or do we have enough information to find Fq? We have the radius. Good. What is the radius? Okay, so what you're telling me is you're going to make a stab at the equation of kind of like subbing in everything in the equation. What's the equation we're going to use, though? Okay, this has got to be rock solid. This is your old friend. This is just like the gravity one, right? Just like the gravity one. Okay, Q1, Q2, R squared, right? When it's force, there is two charges and a squared radius, okay? Yeah. Why? Yeah. What does it say? Yeah. So we could say Q equals Q1 equals Q2, right? It's kind of like they're all the same charge, and let's just call that Q. Okay. Okay, so then Ft we know, sine theta we can kind of like plug in at least. Times the sine of 5.7 K Q squared over, and K is a constant, so we can even plug that in. What is my R squared there? Or what? To what? Squared? This is where your work to save yourself from before. Exactly. This is a perfect example of why that work is valuable, right? Because once you get into the momentum of just kind of like, okay, and what is it? Plug it in. Like you're not thinking to check its units, and that's not the time to think to check its units, right? Okay, awesome. So then 0.02 squared, right? Is it 4 or 2 or 1? Like, is it D? Is it D over 2? Is it 2D? What is it? Like the radius that we're using. Are we using just D as the radius, or is it D over 2, or is it like 2, is it 2 times the radius or something? Or 2 times D? Like, because for this right angle triangle that we created, we use D over 2, right? Let's just see. What is R supposed to be? What is it supposed to be? A distance between them, right? Like, forget about this right angle triangle, right? Like, there's no need to cut it in half or any of that, okay? So that's something I've seen people kind of get hung up on too. Sorry if that was like, but it's good when you're kind of like, wait, what? Why is that even a question? Like, that's good. It means you're not even thinking that. Okay, so then this is just kind of a rearrange, right? Okay. So let's just see if we get to the same values and let's make sense of it. Which is tough because we're not as comfortable with coulombs as we are with like meters and seconds and stuff, but doesn't mean we can't use a little bit of knowledge. Yeah, that looks about right. So, sorry, just give me 1 second here. Oh, is that for q squared? Okay. It gets nasty when you do like scientific notation in it, right? Have you ever seen like how to combine the scientific notation parts and how to combine the number parts so that you don't have to do them at the same time? Okay, okay. So if I take this, like this is a good example here. I could take, because these are both multiplied, I could take that as 4, let's just use 4.7 and 8.9 or whatever. Yeah, 8.9. Like I could do that fraction times this fraction, right? Do you agree that that's the same thing? Yeah, multiply on top, right? So now I could do just that division on my calculator, and I can just write times 10 to the and solve this one. -8 divided by 9. What's the rule for these exponents? Do you know? Do you remember? Exponent, you got to remember your exponent rules. You're going to do this way. Exponent rules. So division, we subtract. Multiplication, we add. That's pretty much all you have to worry about. Okay? Square roots, we divide by 2. So I can even do it for square roots. I can do the square, like if let's say I get like 6.5 here times 10 to the 4, I could do the square root of 6.5 in my calculator and then just write times 10 to the 2 because that is the answer of times 10 to the 4 to the power of 1/2, which is what a square root is, right? So you can like completely eliminate the scientific notation part of plugging into your calculator. You do have to be careful and like kind of pay close attention and do some extra rearranging. But especially for those where you're like, oh, this one's not working because of the scientific notation, it's worth it to use this method. So this would be, 4.7 divided by 8.9. So let me actually use the numbers. 4 divided by 8.99. And so we get, and now this is the other thing. I'm going to have to move my scientific notation a little bit because it'll look funny if I do this. 0.5 times 10 to the, right? We don't do that. We do 5 times 10 to the, right? But this will be -17, so we subtract the 2. And then I'm going to borrow one more from there. So I'm going to kind of like hide one more away in my 10 to those. So it's going to be a times 10 to the -18. Okay. And obviously, you don't have to do that, right? But more and more, that I think will become easier and easier. So it's good for you to at least see that's possible now. Okay, so yeah, so that's, I mean, I don't even know if that's worth it to, oh, wait, that has our answer. So that is that number. And now we have to square root that number, right? Okay. Okay, let me see. I got 2.29 times 10 to the power of, oh, no, sorry. Um, Again? Okay, yeah, because the square root of that is 1.62. Right? Good? Okay. Okay, so yeah, I mean that's like a lot of rearranging, and so that's where the squared can kind of like hide in there and make it look a little nastier, but yeah, I mean definitely like tough, but I would say besides, and this is even maybe just a little bit of a miscommunication between you and I, because you didn't even have it really wrong, but it felt like you kind of like had your, your crumb trail to follow the whole time. Did you feel that? Hmm. Hmm. Right, and compare your answer and stuff. Okay. Okay, yeah, it's tough without it. So you have it now, right? Okay, hit me with another one. This is good to have these ones that are like this. Yeah, no problem. Hmm. Okay. Yeah, this is definitely an interesting one. Okay. So, and so have you tried this one? What's your sort of status on exposure to this one? Just sort of taking a look. Okay. Okay. So let's like this, even took me a kind of second read to even see what was going on here. So let's take a couple reads, see what we can get out of their question into our sort of givens, and maybe if we can find a crumb trail, or maybe we can at least see something that we can, that looks familiar that we can kind of like get some more information on, a free body diagram, or start to explore a bit. Okay, so I'll give you a minute here, give it a couple reads, see what you can highlight. Okay. Okay. We got that they're neutral. Okay, so you've got more. What's the setup here? Is there strings? Are they hanging? What's the deal? Okay. So we've got sort of like how many spheres? Two spheres. Okay. Do you know how far apart they are? Are they touching? What? Okay, good. Nice. I like it. Even converting that. So 0.15 meters between them. Okay, I like it. And they're neutral. Okay. Yeah, the mole of carbon, it looks like it matters. It doesn't. It doesn't. If I just told you a sphere contained this many atoms or this many electrons, that's what you could do this entire problem that way. You wouldn't need a mole. The mole there. But if it was needed, it would be extremely unfair and it would be fully a chemistry question that would not pop up here. So you like it's almost unfair to give you everything you need to know about the mole because it's a whole concept. So they won't really do that. Like it will be it'll just be a smokescreen. You can do everything without it. Okay? So we know how many electrons are in each, right? Can I ask you this? What what do they ask for? What will our answer be? Yeah, yeah. Mm-hmm. Okay. For FQ to equal FG. Yeah? Well, ooh, okay, okay. So this is more so a problem with. So first of all, is there an FQ? Is there an FQ right now? One word that you can point to say yes or no. No. Why? Neutral. So if they're neutral, they don't have an FQ. So it can't be equal to the FG, right? Can I ask you, what FG is this? Is this MG for each of them? No. No. Because it doesn't just say their gravitational force. When I say gravitational force happens between how many things? Two. If I just say gravitational force, you're safe to assume who the other gravitational force is. The Earth, right? What is it? Yes. Absolutely. Yeah. Mm-hmm. Mm-hmm. Yeah. Okay. That sounds like a pretty good crumb. You found half the loaf there. So let's follow it. Let's follow through with that. Okay? Like yeah. Yeah. I mean, and this is one of those things, right? Where like the only word that I could really point to is that to say no, no, right? And this is again like that last one. The word equilibrium was like the whole problem, right? And so sometimes it does come down to those one word things, right? I so first of all, to say it's sneaky, I kind of agree with you. I kind of don't. It's sort of like, the student in me agrees. The teacher in me says that it's it's our job to sort of like show you the tricky ones because the easy ones are going to be easy, right? Like that's kind of the trick. That's the problem of the relationship of kind of like presenting problems. You're never really going to get to the point where you're just doing problems that you feel really, really good about for hours and hours because that's a waste. You want to be putting that time into challenging yourself to learn more, right? Like it means you've learned that concept pretty good. But what that means is that you are always in this state of like, oh, just grasping and all this stuff, right? Which really puts the mental stress of confidence and all that relationship into account, right? So, okay, anyway, sorry. Enough of a rant there. So you have a crumb. I'm going to leave you here. See if we can get to, and we don't necessarily have to get to a fraction, but even just sort of like something about the electrons, right? Okay, get me there. Mm-hmm. Good. Yeah, doesn't even matter actually. Okay, so you got that that their equations kind of get to this point, right? You got to this point, right? Okay. Do we know anything about um okay, so you canceled the R's, yeah? Okay. The K's and the G's are going to kind of work themselves out, right? Like they're just numbers. But what about Q1, Q2? Are there different charges or the same charge or what? Yeah, spheres are identical. Good. So we can sort of say K Q squared equals G M squared. Okay, do we know the mass? Okay. Mm, yeah. And they're asking what fraction of electrons would have to be transferred, right? So that's kind of like do you agree that the equation to sort of figure out the fraction, let's say we figure out whatever the charge is, right, that of the thing, then it's going to be over the total charge of like all the electrons. Do you agree? Like those are the number of electrons that left. It will be, but to do that, we'll do a division of, something over the total. That's how you find a sort of what fraction of the total, right? Okay. So I'm just sort of like qualifying that that's what we're gonna figure out right here, right? Okay. What that means is let's um I wonder if we could sort of like say if we knew that this was all of the electrons, let's just assume that all of the electrons went, we could figure out what the mass was, right? No, but then, yeah, because then it's, okay, so I'm trying to do this without the chemistry. You actually could do this very easily with the 1 mole of carbon, which is the problem, right? So, yeah, I don't think it's going to either. So, okay, so let's see if maybe there's something else. Yeah, yeah. Yeah, I mean, we kind of already did combine the equations, right? So like in some sense we are using the two equations there. We did also, like technically we could say that we're doing like this, right? And actually one is negative of the other, right? Do you agree with that? One is negative of the other? One of the So if they're electrically neutral, then if one loses electrons, the other one has to gain electrons. The one that loses electrons is now positive or negative? The one that has lost electrons. Yeah, so now we have a positive and then it gave its electrons to something else, which now has extra electrons, so that's negative, right? So if this thing does this type of transfer, right, then this is now positive. This is now negative. Okay. Yeah. Yeah, because we're transferring electrons from one to the other, right? Um, but yeah, I'm very tempted to just sort of, I mean, because this is actually the definition, which does make me maybe think that it is the case, because the definition of a mole comes from carbon, but 1 mole of carbon is 12 grams of carbon. Like that's kind of where a mole came from, in some sense. Yeah. So if that was the case, then we could use that in our masses, and now we could solve for Q, right? Yeah. Yeah, it's definitely like a little unfair. I'm just trying to think if there is any other way that we can kind of approach this. Um, Go ahead. I think honestly, like this is how I would do it. generally also when there's a fraction idea, we can get away with saying we can do like a sort of like division of one equation by the other, if that makes sense, right? So, okay, so check your formula sheet then. Maybe there's actually this on your formula sheet. Is there a gram per mole mention on there? No? Okay. Yeah. Do you have the elementary mass or mass of a proton, mass of electron? No? Wow, that's a little strange. Okay, so that means you're probably not going to be doing an oil drop experiment, which is interesting. Yeah, yeah. You did do that? Okay, interesting. Oh. Yeah, I mean that's pretty close, right? An atomic mass unit. Yeah, like I would be interesting to see it because like and like, especially once you have the understanding of this, it's like, oh my God, this is so easy. I don't even want to try to do this another way. It's just like once we have that, we have the mass and we're good, right? So then we would solve for Q and then kind of like divide it by that to figure out the fraction, right? It is interesting that they give us this distance when we don't even need the distance. Oh, you have his solution? Awesome. Okay, cool. Yeah. Okay. Yeah. And he might have sneakily done this. Like, there's actually a few different ways that I could kind of like sneak this into the question without actually saying this about carbon or about 12 grams or whatever. We could have also, so I don't know if you've done mass charge ratios, right? Like mass spectrometry. I don't think you've done that yet, right? You haven't done magnetic fields yet, right? Okay. Okay, so that's when you'll do magnetic fields and mass spectrometry. I just have trouble with that one. And that's when you'll talk about mass to charge spectrometry. Yeah, it's hard. Okay, did it send? I didn't get anything. Let me refresh here. Oh, there we go. Oh, wait. Oh no. Oh, okay. It came and went away. Okay, here we go. Yeah. Right. He used he used 0.012 kilograms for the masses. So that's 12 grams. He just snuck it in there. That is sneaky. Yep, he did this. He used it without even telling you. Yeah, he just snipped it in there right at the last thing where he solves, where he plugs in m squared there. You see it? You'd never know. Yeah, exactly, right? Yeah. Yeah, I know. Show your work, eh? Where's that mass come from? Yeah. Yeah, yeah. Okay. So he kind of like threw this all into one equation, right? So I just kind of want to show you that method too, where like whatever charge you get, it's going to be some multiple. So that n is either like 1, 2, 3, 4. It's not 1.5. It can't be 1.5. You can't have 1.5 electrons, which means you can't have 1.5 charges of an electron, right? That's the charge. So every charge that we see in the world will be a multiple of the electron's charge, right? Does that make sense? So if you see a charge of 2, that actually means 2 electron charges, right? It doesn't mean 2 coulombs, right? Because coulombs is the unit of charge. But when we say like a calcium 2 plus ion, right? I'm saying the charge is 2, the n value is 2, and the E is the electron's charge. You agree with me? Do you agree that I can't have less than the electron's charge? Yeah, like if I tell you that there's an ion here, you say, well, it's either a plus one or a minus one then. It's not a minus a half or a plus a half. It can't be, right? And that's what the one and the two and the half and that we're just saying, that's what that references is how many electrons have been lost or gained, right? It is kind of a constant. That's why it's called the elemental charge, because it's kind of like some like fundamental idea about the universe that like every charge you see will be a multiple of this value because this is the smallest unit of charge that we have, right? Okay, so then yeah, so then he just throws this in for Q and now it just kind of rearranges and but yeah, that's what we're just saying now, right? It is measuring coulomb, but it could be just how many electron charges do you have? And that's what n is. How many electron charges do you have? If n is 5, then you have 5 electrons charge worth. He just used this equation and subbed it right in for Q here, and so we ended up with n squared e squared. And now what's nice about that is n is going to be a nice number that we can solve for. E is a number that we can use our formula sheet for and just plug in as a number, right? Yeah, that's cheating. He didn't even mention it. Snuck it in there. That's almost slimier, right? Because it's like it's not even going to mention that they need to know this. So yeah, so he does this and then he rearranges oh, and says, we're really solving for n or n squared at least at the start, and so it's g m squared over k e squared, and then we square root that. And this will be the number of electrons, right, that have in the charge, right, causing charge, or you know what I mean by that, right? Um, and then that we will compare to our starting value of how many we had, right? Here, because that's the total number we had. This will be the number that kind of got transferred, and then we'll come up with a fraction based on that, right? So the fraction of electrons. Hmm. Yeah, it's a little sneaky, right? Yeah, I think that would be a strong hint too, right? Like you would go from there when you got to this stage and you're like, wait, I don't know what M is. You wouldn't have gotten to that point without knowing what M is, and you say, oh, I know M. G and K are both constants. I can find out what Q is. Now I have a crumb to get, the fraction. Right? Yeah, that's frustrating. But I mean, that's good. So what I'm here for, right? Like that was kind of our suspicion, and otherwise we wouldn't have known that, right? Okay, cool. So let's see if we can try one more before we go here. That's okay. Yeah. Maybe like more of a communication type question too. Feel like we haven't. It's like remember we kind of have to hit Kika right on our test. Knowledge inquiry, communication application. The tough thinking, the strange, the weird questions like that one was a thinking question. The knowledge ones are just like testing your straight kind of like formulas, nothing too wild. Um, Inquiry is generally like a little the tougher, the thinking inquiry ones. But communication is a whole section of like graphing and writing, like definitions and telling like what's, like what really? Oh, that's nice. So when you like, do you get on your test, do you see your breakdown of Kika? Oh my gosh, it's so annoying. Ugh. Oh, just feeling. Sometimes, right? It feels like that. Yeah, yeah, yeah. Uh, rereads the whole thing is wrong. Wow, that's a yeah. I mean, I didn't know that they could do that. I thought they were kind of like restricted to use Kika because I think it's I think I don't know if this is true, but I think it's like your right to know where you're getting your marks from, like something that they did to like so that teachers don't just kind of do what you're saying and just be like, and I think it came from like teachers being like, I don't like this kid, I'm just gonna like make up that they did bad or mark them harshly, right? And so I think that's part of it, right? Okay, that's probably where your knowledge comes from. I don't think your communication would come from there, really. Like communication, yeah, would come from like anything that you're like writing an answer rather than like doing math for the answer. Really? Oh my gosh, he's cheating you. It's generally good because those are usually a little more boring and a little more like theory based stuff, which isn't as nice and fun. So that's okay. Hmm. Right. Okay. Yeah. Okay. Interesting. Yeah. Ooh. Projectile. Okay. Oh yeah. Yeah, this is definitely a question type that you should kind of like get comfortable with and be ready for. So we can kind of like take an energy approach to this as well as a force approach to this. Okay. Um, mhm. Mm, okay, that's nice. That's valuable to have. Okay, so let's sort of see this problem. And you said it's a projectile motion problem, right? And it looks it, but how do you know it's a projectile motion problem? How do you tell if something is a projectile motion problem? Do you know? Okay, so it's got that certain look of the like parabola, right? That's it. Yeah, exactly. Okay. So they tell you a few things here, right? They tell you um the electric field strength, right? And so that's 0 times 10 to the 5. And can I ask where is it that value? Because generally we kind of point to a certain spot and say say the electric field is this. Where is it that value? Where is it that? Yeah, in between the two plates. So this is the thing about these two plates like this. They set up a perfect uniform magnetic field in the middle where anywhere in this box, the value is that amount. It doesn't matter that I'm closer to it here or here. The value for the magnetic field is the same no matter where I am in this box. Okay? Okay, well that's a lot like the box that you and I live in gravity, right? Where no matter where we are on this planet, we feel the same force, right? Well, this isn't quite a force yet. How do we make this a force that affects the proton? How is FQ related to electric field? What unit am I asking you about? I'm asking you about the unit of newtons. And the unit you have is newtons per coulomb. So what do you need to find newtons? The number of? Yeah. So this is just Q, the charge that's experiencing it, times the magnetic field that it's experiencing. Yeah, that's one of your formulas, right? Okay. So then, where do we go from there? So we have a force now, kind of like the gravitational force, right? Okay. Wait, what Q would we use there? Yeah, the positive elementary charge, right? Good. Okay. So then, where do we go from there? Have an FG. Okay, let me take you out of this unit for a second. Let me tell you that I've got a cannon, okay? Your old friend, right? And it's going to shoot a ball off of a ledge, and we're going to catch it 12 meters later. And I want to know how far it's fallen. What do I do? And I tell you that the velocity here was, don't look, 1.5 times 10 to the 7 meters per second. And this wasn't 12 meters, it was 12 centimeters, right? So let's just tweak that. Okay, so what would you do in this problem? Yeah, but this is the projectile motion back to kinematics, right? We have to do, yeah, yeah, V1, V2, A, delta D, Y, right? These are Y, V2, Y, and then delta T. Okay, so let's go from there. What do we do? Uh, dy, yeah, delta dy, right? Okay, so we want to solve for this. Do we know A? Not quite. We don't know G, right? It's not G. It's not G. No. Well, it is, but this could be the vertical view, and this could just be moving to the right, and my two horizontal plates could be like held vertically, and I could be looking from this angle. Do you agree? So in that case, then we don't have to worry about gravity, right? Okay, so then what is the acceleration there? What's causing an acceleration? There must be an F net. Newton says there must be an F net if there's an acceleration. And where's the F net? Who is causing an unbalanced force? FQ, yeah, FQ, the force, FQ, right? So then we can solve for, um, no, no, yeah. So we can say FQ is equal to F net, which is equal to MA. And I think honestly you're gonna have to use the mass of the proton. Okay. And then we can solve for acceleration. And then what? Yeah, and actually time's going to be the connection to get us to the x. Because we know Vx, and do we know d delta d actually? Delta dx? Yeah, we know it, 12 centimeters. So we can actually find delta d that way, right? So, um, okay, so yeah, we can solve for delta d, plug that in now. Now we don't have to worry about it, and then we can use that to solve for no delta dy. Okay. Okay. For this one, yeah, in the x, yeah. dx is equal to delta dx over delta t. We'll solve for delta t. Sub it into the y, and then solve for delta dy. Right? So that will be delta dy is equal to v1 initial delta t plus 1/2 a delta t squared. What is the v1 initial? Yeah, it's vertically. It's not traveling any speed at start there. Right? So that's it. Yeah, and your time. That's it. When the oh yeah all the like the earlier unit you mean I thought you meant like the dimensions, the meters, the seconds. No, what the yep. Kinematics won't ever go away. That stuff is like something that we can always pull out because speed is a connection, and then we have energy, right? And energy is always connecting to everything. So now we can go back to kinematics through speed. And now this is energy, so energy's everywhere, and so we can go back to kinematics through anything. Yep, this is the definitely like the type of question that you'll see, and it won't necessarily always be kind of like like a kind of perfect case like this. It might be an energy scenario where I'm kind of asking like, how fast is it going here versus how fast does it leave? Well, then it's just about how much energy did the plate give it, right? Yeah, then I would do the energy approach. I wouldn't care about kinematics, right? So you got to kind of ask that question of like, what's gonna get me there, right? Like here, the delta D there is restricting you, and like V and delta D, that's calling out for kinematics, right? But if you don't have to, use energy first, and then if you have to, use kinematics. Okay. Okay. Cool. Good work tonight. Okay. Do you feel like this is like coming in a lot more like solid? It's sort of things you're getting ideas of what to do as you're kind of going through the question. It seems like as we go through the question, like you're seeing the layers as they're getting peeled back, like a lot faster, a lot easier, a lot sort of like there's a lot more transparency to those layers, right? Where you can see a few layers deep now, right? Which is a big part of physics, right? Knowing where you're going. Um, Okay, awesome. So I'll send you our note from today. Is there anything else that I can get you? You looking for extra practice problems or anything in this stuff? Yeah? Okay, I can get you some. Absolutely. Hard or easy? Right, but just not what he does. Not what he uses. Mm-hmm. Mm-hmm. Okay. Okay, so let me just make a little note. I'm gonna send you some, okay? Yeah, no problem. Um some true statics. Okay, cool. And I just wanted to check in, like, do you have an idea of a test on the horizon? Yeah? Okay. So then what do you go ahead, sorry. Okay. Okay. Right. Yeah, waves is actually a little bit of a shorter section, but there is some crazy stuff that happens there that will well, so I mean, this is something that you will talk about, but light, so you've talked about electric fields, right? And a plate like this, you can imagine if I hooked up, so do you know what alternating current is? You've heard that term before? Okay, and you've heard direct current, yeah? Okay, direct current is just like a think like a water tap when I turn on the tap and water comes out. Direct current is that, but with electrons. Instead of water molecules, it's electrons coming out, right? And so the thing that matters is that it's a bunch of charge coming out, right? But it's like all charge just going in one direction is just like a big hose of charge, right? And so it kind of like builds up and builds up. The problem with that, it gets dangerous if you like accidentally kind of like there's a leak or something, it'll just like keep going. Okay? So it's dangerous. So anyway, everybody uses alternating current now, which fluctuates and your it's basically like the positives and the negatives of your plates here. They constantly like switch back and forth. So that the electric field is like up and then it's down and then it's up and then it's down and then it's up and then it's down. So it's kind of like I go with the electrons, I go through the circuit and then I come back with them, and then I go through with them and then I come back with them. Well, what does the circuit feel? Electrons coming through it. It doesn't care that it's one direction or the other. Okay. Okay. So to our point of waves having to do with magnetic fields. So light is actually it's a fluctuating electric field. As it travels, in the space, in that little box of space that it's traveling through, if you were an electron in that space, you would be attracted up and then you'd be attracted down and then you'd come back to normal. And that's what you would experience if you were an electron. It's kind of like if you were in the water, if you were a beach ball, you go up and then you come down and then okay, now that wave just went through me, right? That's one part of light. The other part of light is a perpendicular, so electron electromagnetic field is going up and down. Sorry, electric field is going up and down. Magnetic field is going left and right. Okay? And that is what light is. That's what light is. Like we don't know what's going on or why it's like that, or like the why is not really for us to answer. It's a perpendicular. So can you see it? Like the orange one is meant to be kind of like horizontal compared to the, right? Can you see that? Like this is meant to come out of the page and then into the page and out of the page into the page, right? So that's what light is. It's a fluctuating electromagnetic field. Have you ever heard of the electromagnetic spectrum? Electromagnetic spectrum is the spectrum of light. That's what light is, right? So wow, it's crazy, right? Like I don't know, like light is definitely a strange thing, and you're actually going to learn a lot more of the strange things about light. And in fact, because of the strange things that have to be true about light, there's strange things about us that we just don't notice. Like we are always vibrating. Like every particle is always shaking just a little bit, and you could figure out, but we're just so big that you can't notice it. But little tiny particles like electrons, you can't quite nail them down. They're you can't say that it's exactly here. You can't spot them because they're too yeah. It gets weird, okay? And it'll get weirder. But for now, that's the kind of relationship, okay? Okay, cool. So, awesome. Yeah.